Okay, welcome back to CHEM351. We are shooting a video that's meant for Monday, March 23rd. Remember, Friday is spring break holiday. They're keeping that. The video for this last week's already on YouTube. Make sure you see that for chapter 10. A number of dates here coming up. We've got a very busy day coming up on Wednesday, as you can see here. Well, first of all, homework 11 will be due tonight. Sorry, that's homework 11. We're kind of compressing this chapter 11, so we're actually going to finish it in this video here, and so this will be due tonight, homework for chapter 11. Remember, that's the last chapter, getting ready for test 3. Test 3 will be available on Learning Suite as a PDF, 40 multiple choice questions, starting Tuesday, March 24th, it'll be there. But you need to upload your answers, and there'll be a sheet that you'll fill out your answers and scan it, or take a picture of it and make sure you upload it the normal way, like we've done with the homework before, so it shouldn't be too big of a departure there. But it'll be 40 multiple choice questions. We'll also have an exam review video that we'll shoot for Tuesday. We'll answer questions on sample test 3. Some people have already been emailing me about that, and I'll go over some of those questions that people have asked about for sample test 3. Also quiz 7, which is also due on that same Wednesday. Sorry about that. It's like the take-home quiz before. Just print it out, do it, and then scan it and upload it. The quiz buttons are now active for uploading to Learning Suite. It's an open book quiz, get all the help you want. But remember, test 3, the exams and the final are not open book. You cannot use any other resources there. There will be a data sheet. If you've been working the problems and practicing well, it should be similar to what we've done in the testing center. And then we'll start chapter 12, also on March 25th. So we'll have another video for you on March 25th. And then that's the last section. Remember, we'll have chapters 12 through 15 for test 4 at the end there. So if you have questions on this, email me. There's a new revised schedule. Make sure you can see that. It's got the new dates and the new groupings of some of the chapter topics. And also here's quiz 7. Make sure you can see that on Learning Suite. That's there to get a hold of it. All right, so let's go through the topics here for chapter 11 and the different things we need to look at here. So topic-wise, these are now alkynes. We'll have very similar reactions that we looked at before. We'll do a little bit on naming, not much. These are named as alkynes. Enines is where we have an alkene and an alkyne present. The alkene gets precedent there. We can also do inols, alkynols, which have an alcohol. The alcohol always gets precedent there. We'll just do a little bit on naming. Some interesting compounds, I'll show you a couple of those. Preparation is the double E2 elimination to put the triple bond in place now. So we'll review a little bit of that, not much though. And then the reactions are all electrophilic additions. All the reagents, we'll just use the 4 main reactions: hydrohalogenation, halogenation, hydration, and hydroboration. We will not do the halohydrin reaction with the alkynes, but hydrohalogenation is just with HX, HCl, or HBr to make the vinyl halide. And then addition of a second equivalent, you can form the geminal dihalide here from the alkyne. Halogenation, same thing as before with bromine or chlorine, getting the dye. Halo, and it's the trans product there. So that's really the only one where we've got to worry about stereochemistry. And then if you add a second equivalence, you go to the tetrahalo product. Now, the difference here with the alkynes is the hydration and the hydroboration. So hydration here, if we protonate and then add water, we initially get this vinyl alcohol called an enol. Now that will tautomerize. We call these tautomers. These are stereoisomers that only involve the movement of a hydrogen atom. So notice the enol here has the double bond, the pi bond between carbon and carbon, whereas the ketone, or the carbonyl here, now remember that functional group, has the double bond between carbon and oxygen, and this hydrogen's moved over here. This carbon adjacent is now a methylene. So we call those tautomers. It's actually a common effect with a number of functional groups. We'll see it later on with the DNA, RNA bases, also have tautomeric forms. But this is Markovnikov. We'll form the Mohr substitute carbocation and get the Mohr substitute alcohol if there's a choice there. And then the last reaction, hopefully, hydroboration, where we get the anti-Markovnikov, the less substituted vinyl alcohol, and actually this will then go on to an aldehyde product if it's a determinal acetylene. And this is the useful reaction with borane. Hydroboration with acetylene will do the hydroboration, addition of hydrogen and borane, and notice that's anti-Markovnikov, boron at the less substituted carbon, and then oxidize that carbon-boron bond like we talked about last time to an alcohol, and there's our tautomerization again to the aldehyde. Now, acetylene alkylation is also a reaction where we talk about a lot of synthesis ideas here, and that's because there are a number of bases known that can deprotonate acetylene and form the acetylene anions. Those become good nucleophiles. Remember, that's from chapter 8, going way back. And then we can do what? SN2 type chemistry there to alkylate acetylenes. We can even do it on this side too if we treat with another equivalent base and a different alkyl halide or alkyl tosylate. Or we can treat the acetylene anion with an epoxide. Remember, this is a charged nucleophile, so we're adding at the less substituted spot, popping open the epoxide, then protonating the O- with water. That's a subsequent step. A slash needs to be there, and then we get the alcohol with an acetylene in there. So we'll talk about retrosynthesis and how we can use these in multi-step syntheses coming up. So let's go back and go through the reactions a little bit, and also maybe start out with some nomenclature, or maybe just some general concepts about alkynes. Maybe we need to review that. So remember, an alkyne is what? It's a carbon-carbon triple bond. And what is a triple bond? Propyne or acetylene here? Well, it's got what type of hybridization here? That's right, sp. Okay. So we leave behind what? 2p atomic orbitals on each carbon. Well, the S and the 1p is mixed to form the sigma bond framework. These are the black bonds, right? So we have an sp hybridized bond over here, bonding in this case to a methyl group. And we have another sp orbital over here, bonding to this hydrogen. And then what do we have? We have the sp right here, where my fingers are. Also, that's a sigma bond between the two carbons. Remember, sigma bond density is on the axis. What do we have left behind? If these are sp hybridized, we have 2 p's in each case left behind, right? And that's the pi bond, both top and bottom. That's one pi bond where my hands are. And then perpendicular to it is the other pi bond. Remember, p atomic orbitals are mutually perpendicular. So we have 2 pi bonds and 1 sigma involved here. Now the name for these is alkyne. And so if we have an alkane, we take off the ane and add yne. Okay, so there's our new suffix. So this came from 1, 2, 3, the longest chain, propane. So this is propyne. You don't need a number here. Propyne can only start on either side. Numbering wise, that's the 1 position, and then the 2 numbering through there. Acetylene is either ethyne. Nobody uses that name now. Everybody calls this acetylene. You might wonder about acetylene or welder's gas. Any welders out there? Maybe some of you have done that. It burns at a very high temperature, over 3,000 degrees. So these pi bonds engender a lot of energy to this type of molecule. Let's look at the bond distances maybe a little bit. And these are quite short bonds. So these are like 1.21 angstroms. Double bonds are 1.38, angstroms, and a typical carbon-carbon single bond is what? 1.54 angstroms. So you can see we're getting shorter right there. We talked about that in an earlier chapter. The carbon-hydrogen bonds and the carbon-carbon bonds on the side, because these are sp hybridized, are also a little bit shorter and also a little more stable that way. You don't need to worry about that. That's kind of a detail there. But the shorter bonds involved with the sp hybridization. Why is that? Because it's 50% s character now. The s atomic orbital is held closer there. Let's just jump ahead and see if we can name a couple compounds here that are a little more complicated. So a chain like this would be 1, 2, 3, 4, 5, 6, 7, 8. So this is what? Octane or octine now. And at what position will we number from the end that gives the lowest possible numbering? So this would be 1, 2 position here. So 2 octine. How about if we have maybe a chloride here? So what would be this one? 1, 2, 4, 5, 6, 7. So that would be what? Heptine. And which one gets priority? Well, kind of like the alkene, the alkynes have priority over halides and alkyls. So 1, 2, no, we name it 1, 2 here. 3, 4, 5, 6. Okay, so we need 6 chloro. And then out in front of the heptine, we need what? 2 heptine. So there we go. 6 chloro, 2 heptine. Oh, but this is a stereocenter, right? So we could have some indicated stereochemistry. Let's say that that is a bold wedge there coming out at you. So we would need what? We need to designate that stereocenter also. So what is that rotating? Top priority, second priority, third? So I think that is S. And if you have the one stereocenter out there, you don't need a number for it. Oh, what about the alkyne? Do we need E or Z there? No. The geometry is linear here. Remember, this is what? 180 degrees for the theta angle due to the hybridization using sp hybridize. So there's no E or Z there. There's only 2 groups on the linear projection of that functional group. All right, let's maybe do 1 or 2 more, and that'll be it. I kind of want to downplay nomenclature, so we'll just do a little bit more maybe. How about if we have, let's see, oh, maybe 2 more. Okay, how about this? So we have an alkene and an alkyne. So what are we going to call this? Well, this is in the family of eneines. And eneines are just what they mean. If you have an alkene present, there's the number we'll need for that, and then an alkyne. And then the parent is whatever it is. So 1, 2, 4, 5, 6, 7, 8. So this is an octene-ine. Is that sound going to be a problem? Yeah. So we are back. We got that sound there. So the alkene takes priority over the alkyne. So numbering here, you'd start with number 1 here. So you need a 1 in front of the octene part. That refers to the octene. Then 1, 2, 3, 4, 5, 6, 7. We'd have to stick a 7 right in there. Ine. So it's 1 octene, 7 ine. Okay. There's all sorts of other combinations there. How about this one? How about if we have an alcohol and an alkyne? So we have 1, 2, 3, 4, 5, 6. So we have hexyne, all. Okay. So what gets priority here? Yeah, you're right, the alcohol. So no matter what, you give it the lowest possible number, even if number 1 would start here, if this was the priority. It's not. This 2 position is the alcohol. So 1, 2, 3, 4, 5 is where the hexyne starts. And then the ol position would get, what, 2. So that would be 5 hexyne, 2 ol. And I think that's about all I really want to say about nomenclature there. Okay. you have any more questions on it, we'll keep them relatively simple, I think, on a quiz or a test. So let's see. Let's get into the preparation. So how do we make alkynes? Well, we can make them from CHEM dihalides. Okay. So if you have this 2,2-dichlorobutane and you treat it with 2 equivalents of t-butoxide, or you can use 2 equivalents of sodium amide. Okay, so they have to be strong enough bases. And t-butoxide, remember, is a great E2 base because it's bulky and it's pretty basic, right? The pK of butyl alcohol is 18. The pK of ammonia is 38. That's even more basic, but it's small, so it will function as base, not a nucleophile. So what do you get here? You get the first elimination right here, which is your standard E2 elimination. And that will give you the vinyl chloride. Remember, we had a word for groups directly on alkenes like that, so it would be a vinyl chloride. And notice we still have another hydrogen here. So another equivalent of base can take that off, and that's set up directly to go to what? The 2-butene product. So that's how a lot of those will work. You can also have the 2 halides and 2 leaving groups on adjacent carbons. They don't have to be on the same carbon. We call these vicinal, geminal. Geminal groups are on the same carbon. Geminal from gemelos or Gemini, which means twins, right? Or they can be vicinal to each other. Vicinal leaving groups are 1, 2 on adjacent carbons. They're vecinos or neighbors, if you remember your Spanish. A little bit different here. But also the 2 equivalents of base here. We can have 1 base, pull off 1, and then we'll get what, the vinyl bromide in this case, and then the same thing here if we get another equivalent of base, taking that off, and a similar thing. Okay, so yeah, preparation is that way. Another way to prepare alkynes is to use acetylene anion. So acetylene anion, and we can deprotonate acetylene. Again, the pKa here is what? pKa is 25. So if we have a strong enough base like lithium amide, okay, again, the nitrogen anion can deprotonate that and form the lithium acetylide. And when we draw it as a metal covalent bond, remember you can also have this plus charge and a negative charge here. So it doesn't matter, same thing. You could draw it like that. Okay, same thing. And then we can add an alkyl halide. Let's say this group here. And so if we have this attack like that. So there's our nucleophile. It's small, it's charged. This is primary. They work best for primary. And then we get what? We get the acetylene product. Okay? We get the propyne product. So that's a very useful procedure for forming those type of products. All right, let's get into the reactions. Let's get into the electrophilic additions here. So first we'll look at hydrohalogenation, and then we'll do halogenation, hydration, and hydroboration. Okay. So here's our first one. Let's take butane and treat it with HCl or HBr. Those are the main ones we're going to look at. And if we just have one equivalent, we're going to go to the vinyl chloride. And you see we've got what, the top priority here, lower priority there. At each carbon, we need to analyze this. So we need to apply E or Z here, right? So look, the methyls are trans to each other, but the priority is such that you look at this hydrogen and then this. So the top priority on this carbon is this methyl. And you examine the priority here, and the top priority is the chloride. Position in the periodic table. Notice these are together. So what would we call this? It's E or Z. Which one is it? If they're together here, that's Z, zusammen, okay? But notice the hydrogen and the chloride that we just added across here came in trans to each other. That's part of the mechanism. Now if you add another equivalent, do hydrohalogenation here, you get the geminal dichloride, the two chlorides together, the 2,2 dichloride. So our mechanism, we've got to come up with something to figure this out, right? So let's see. Before, we always added electrophiles here. So our electrophile in this case is going to be what? A proton, H+. So let's go ahead and pull those electrons out of one of the pi bonds. That's going to create a carbocation here. But notice that would be a vinyl carbocation. We're not going to do that. We're going to do a concerted reaction now, where as the electrophile attacks, an equivalent of chloride or weak nucleophile can come in here and attack. And you see that will give the hydrogen and the chloride trans to each other. Now you can do the mechanism like this. You can have the HCl reagent up here getting attacked, you know, like we did before, and then a chloride coming off another molecule of HCl in that manner, okay, to deliver the chloride nucleophile. This way we avoid carbocation, because if we did it just the first step there, we'd have this. Now your book kind of sloughs over this mechanism, kind of waves hands a little bit. This would be a problem. This is an sp hybridized carbocation, a vinyl carbocation that does not benefit from hyperconjugation and stabilizing effect. It looks like it's secondary, okay? But because of its geometry and its sp hybridized, that's a problem for the stability here. It's most likely this type of a mechanism which involves a collision of three things together. We call that a turbomolecular mechanism. But it gives the product that we've seen before, okay, hydrohalogenation. So it's not too bad there. The next one, let's see what we do. Let's add our electrophile again. We'll get a second proton on there. We've already got a chloride here. And we've got a carbocation. That's just like we saw before for the hydrohalogenation of alkenes. So this is an alkene. So we're just doing this. Now why are we drawing the proton over here and the carbocation there? Well, this carbon has what? 3 groups on it. So it's really a tertiary carbocation. And plus, there's lone pairs right here on this chloride. Let's go ahead and draw a resonance structure there that would look like this. Now we have the plus charge out on chloride. This resonance structure helps the regioselectivity of the second hydrohalogenation. Alternatively, if we put the proton here, we'd have a secondary carbocation. Yeah, that would be stable, and then we'd form the second chloride going on at the adjacent position, not the geminal position. Okay, so this rationale for the mechanism, the first addition, vinyl chloride, then the second addition, the more substitute carbocation, like we saw before, even though this is inductively withdrawing, because chlorine is electronegative, and it is pulling electron density out of the sigma bond, but these lone pairs are part of the pi system that can stabilize that empty p orbital. So that's a resonance effect that really dominates here to give us the geminal product there. Okay, questions on that? Yeah, Isaac.
So in the first part of the mechanism, why isn't it possible for the chloride to attack on the same face that the alkyne attacks the proton and get syn addition?
Yeah, so you can kind of think of this like this. So here is the pi bond, right? So that's the filled orbital. 2 electrons are going in and attacking the proton, the empty orbital here, which this is an empty 1s orbital. And as that comes out, what's on the back here is the pi star. So the pi star, and it's also a steric argument too, but this is on the front here, the more favorable attack will be from behind to give you the Z product. But that's a good question. Don't worry about this too much. Again, like I said in the book, they don't have very much detail there. But the second step, I think, is a little more clear, which relates to what we've seen with alkenes before. Okay, let's look at halogenation, our second reaction here, which is going to be this. Let's get some more room. And this will be very similar again to alkene halogenation. Don't need to worry so much about stereochemistry. Let's do chlorine. We could also do bromine. Just like before, we could have done HBr, but now we're doing chlorination here. If we just have one equivalent, we'll get out the dichloride, okay? And that's just one pi bond undergoing chlorination. We'll have the same chloronium ion and then backside attack to open up the chloronium ion to give us the dichloride here. And then if we have a second equivalent, or if we just draw a 2 in front of the chlorine or the bromine, we can go directly to this product. And this looks kind of crazy. 4 chlorines on there? Yeah, we'll count them all up. There's 4 chlorine atoms and we have 2 molecules of molecular chlorine. We can look at the mechanism here, which would involve attack on the partial positive end. Partial negative end comes off, and we get this thing. Now, can chloride bridge over and form that chlorinium ion there? Now we've got, what, another pi bond here. So we're just reacting with the 1 pi bond here. That's going to destabilize that greatly, actually. This is a slower reaction than with alkenes. But once we get that, we can then have chloride do the backside attack and pop that open. In analogy to what we saw before, it might turn out to be, though, a termolecular type reaction, which gets around this problem in the mechanism. But as far as pushing electrons, this is fine. The backside attack as this pops open. There might be some vinyl cation character to this. This is a different reagent now than hydrochlorination or hydrobromination, but it goes to the dichloride there. And then what's our next step here? We do the same thing. We can attack there, and we can get the chloronium ion, right? So we'd have that type of species. And remember, we still have chloride anion then from forming the chloronium ion. Then backside attack, and then opening it up. And again, we might have some lone pair donation here and have this pop open before the chloride has to attack. But the end result here is the trans relationship. We would label that not as Z this time, label as E. The top priority group's chloride here over the methyls. So they're across from each other. This would be the E product. This is the favored one. And then this one has no stereochemistry, right? These are not stereocenters now. Don't need to worry about that, but that's how it would arise there. Questions on that? I think that's pretty clear. Let's go to hydration. The next one. So hydration, these are the same reagents, we just have different substrates now, right? The alkyne in place of the alkene. In a lot of ways, these are simpler. The stereochemistry, we don't need to worry about it so much. Well, we got the E and the Z issue, maybe that first step, but with 2 equivalencies go on to completely form the products now. Hydration. So if we have an alkyne, water, and sulfuric acid. Now it's the same hydration reagents that we used before, and we can think of it as doing the same thing, okay? Adding water across here, and first we're gonna get an alcohol. There's the elements of water added there. But we have this second pi bond. You could say, well, we could add water across there, but what's fast at this point is this tautomerization idea. So it tautomerizes, and under these conditions, I'll show you the mechanism. We can easily protonate this alkene, and then instead of adding another equivalent of water here, the lone pair comes down, lose the proton here, and we go to the ketone product. Okay, so this is the different part of that. The first step, I think you're going to see as being pretty similar there. So let's see, what are we going to do here? Well, let's have our acid donate a proton, and that's going to allow for the water to attack. Okay? And we're going to do it concerted that way to avoid that vinyl carbocation. So if we do that, what do we get? There's our proton on there from the acid, and right here, what do we have here? Well, we have this water molecule still there, so we'll need a plus charge, a hydronium ion, vinyl hydronium ion, and yeah, that would be our intermediate, like we saw before. And we have excess water, so we have enough base, a very weak base, but that will give us the neutral alcohol product, okay? The vinyl alcohol in this case. And this is why this is a little bit different now. Before we had a regular alkyl group on there, an sp3 hybridized carbon when we hydrated alkenes. But now when we hydrate an alkyne, look, we have an sp2 hybridized carbon product. And this will tautomerize, like I said, to the ketone. And why is that? Well, this lone pair here, there's two of them on that oxygen, can help do something else here. Another equivalent acid can grab that second pi bond here. It's kind of a continuation of the mechanism, but then you'll see something else is going to happen here. Let's see, if we get to this point, we'll get that hydrogen on there. And what do we have right here now? If we pull that pair of electrons out of the pi bond and form this new carbon-hydrogen bond, what do we have right there? We have a carbon cation, right? Now that's the difference. Under these conditions, we can easily protonate again, and then what can occur? Well, we could add more water here. That would give us a geminal alcohol. But look, these lone pairs are available here to go to what? To go to the protonated ketone. Okay? In fact, these are just resonance structures of each other, you could say. Okay? So once you hydrate an alkyne, some other things happen here. The lone pair, and this is due to the carbon-oxygen resonance energy. This pi bond being between carbon and oxygen is very stabilizing that way. And then what? We've got more water, so we can take that second proton off and go directly to the observed product. Okay. Now look at these two things. This is a carbon-carbon double bond, and this is a carbon-oxygen double bond. Why don't we just isolate this one and not that one? What do you think is more stable? A pi bond between carbon and oxygen, or a pi bond between carbon and carbon? That's right. So there must be some additional stability here for a carbon-carbon pi bond. And why is that? Well, it's because of this resonance that you can get here with the more electronegative oxygen. And this is a major contributor to the actual structure of this ketone. This becomes a more polarizable bond. The electronegativity of the oxygen is higher than the carbon, but this size difference is not big. Oxygen is a little bit bigger than carbon. It's to the right in the periodic table, but this allows for this resonance overlap between the two atoms of different electronegativity, and that's going to give some reactivity to carbonyl compounds. So remember we talked about carbon-oxygen double bonds as being carbonyls. Ketones is one member of the family where we've got two carbons on the side there. We call these tautomers because this hydrogen right here moves down here, okay? And you saw the mechanism of how it goes there. It's because this alkene can get protonated easily because of the lone pair donation into that position. And then, like I said, loss of the proton there can give us the neutral ketone product. So this tautomerization effect is actually seen in a couple other places. I'd like to talk about tautomers a little bit more and show you a couple other examples of tautomers. It is an important concept that we'll see later on. You can have other types of ketones that can form other types of tautomers. So you could have this enol form, or you could have this enol form. This is an unsymmetric ketone. These are both enols, and that's just what the term means, alkene, alcohol, and that's what this initially formed vinyl alcohol is. It's an enol. You see the alkene and the alcohol. they're in equilibrium with the ketone version or the keto version of the tautomers. So it's an example of a complex tautomeric system. Which one is going to be more stable in equilibrium? Well, over 99% will be the ketone version. Okay. Like I said, due to the resonance stability of the carbon-oxygen pi bond versus a carbon-carbon pi bond. Okay. So these enols would be present in trace amounts in a solution of this ketone. Now here's another one to think about. How about this ketone? This is kind of a trick question, we could say. Can you draw the enol version of this? So here's a ketone, again the keto version. The equilibrium here would involve transferring this hydrogen up to the oxygen and putting the double bond there. So what would you get? Let's see. Oh. Now wait a minute, have we seen that molecule before? Anybody remember the name of the molecule on the right? Let's see, yes, it's phenol. Okay. Benzene with an alcohol on it. We've seen phenol before. We talked about the pK of phenol being quite low. It's 10. This keto version here, you could say, well, is this the more stable one at equilibrium, or is the phenol one more stable? Now, we haven't covered aromaticity yet. That's a topic in 352. But having these 3 pi bonds in a ring like this makes this very stable. It's aromatic, we say. That aromatic resonance energy actually stabilizes this form, and this one turns out to be the major form. Over 99%, it will be in the enol form due to that aromatic character. This keto version is actually the minor one. So there's some other issues we'll need to talk about. Normal ketones here exist as the keto one, unless there's some resonance energy, and we'll see that later on with DNA and RNA. If this aromatic character can be borne out, then sometimes the enol version of the tautomers can be figured. So stay tuned for that. Just be able to identify keto versus enol versions. And again, it's just transferring that hydrogen, either from this side up to there, putting the pi bond there, or transferring that hydrogen over there, okay? And that's all we expect you to know right now. Okay, questions on that? Kind of a tricky thing. I kind of hesitated to cover that, but why not? Okay, very good. Let's see the last reaction here, which is hydroboration. And hydroboration reaction is like we've seen before. And now we're going to focus particularly on terminal alkynes. So what do we mean by terminal alkyne? We mean it's at the one position or at the end of a chain. And this is where hydroboration of an alkyne is going to be significant. So here's our reagents. Where we had borane, BH3. Remember that from the last chapter 10 lecture. And then we're going to do the workup or add a step here with base, sodium hydroxide, and peroxide, H2O2. And we're going to get a different type of product. And when I first draw this product, you're going to say, whoa, wait a minute. Well, how do we do that? First of all, what is this product? What's that functional group? Is that another ketone? No, what is this again? That's an aldehyde, okay? Don't forget about that functional group. We've got ketones and aldehydes now available. Ketones come from hydrating alkynes, okay? Terminal alkynes, if they're hydroborated, can lead to aldehydes. In fact, let's take the same substrate here and treat it with water and sulfuric acid. This gives the same thing. We're adding water across here, right? But here, it's going to give a different product. It's going to give the ketone product, okay? But look, with hydroboration, we're getting the aldehyde. And what's the effect here? Well, this one is going to be Markov-Makov addition, whereas this hydroboration is going to be what? Anti-Markov-Makov. So we're going to have to re-examine our mechanism a little bit for hydration with acid and water and compare that to our mechanism for hydroboration. Let's do hydroboration first. Here we have borane, and we're going to do our hydroboration with that same type of mechanism. This is the electrophilic end. Remember, boron has an empty orbital, so we want to put the electrophile on the end. More positive character is going to build up at the internal position, and that's really a hydride going on there. Notice the direction of the arrow. So what's that going to give us at that point? We're going to have boron on the carbon now, and that hydrogen right there. Okay? So that's the anti-Markov-Nikov addition there. The electrophile went to the less substitute carbon, as before actually, all these reactions. Always put the electrophile at the end, because that builds up positive character of that. And we'll see that when we do the Markov-Nikov hydration mechanism, compare the two, right? So hydroboration here, we'll give the boron at the primary position, the end position, okay? And then what? Let's do the workup, sodium hydroxide peroxide. I'm not going through the details of that mechanism. Remember, we just put an OH group in place of the boron, okay? I showed you that mechanism a little bit last time. Don't worry about it. I've never put it on a quiz or a test, but you just do the switcheroo to the alcohol there. That's fine. Notice what type of alcohol is this now? Well, it's that same vinyl alcohol from before, okay? So what's going to happen here? It's going to tautomerize under the basic conditions now, and don't worry about the mechanism of that. Before we showed you the tautomerization under the acidic conditions, but if you have water here, the tautomers can easily reach equilibrium, and the major one will be the aldehyde, and that's what transferring this hydrogen from the oxygen over to this carbon, and then making the carbon oxygen pi bond there. Okay, it's due to the anti-Markov-Nikov addition of the electrophile there going to the end. Well, let's look at the water one here. Okay, so with water and acid, though, we have a different electrophile, right? The electrophile is not boron, it's what? It's acid, it's the proton. So let's do this one. That same terminal group, but now with water and acid. Remember, if you leave out the water, no reaction. Okay, we're going to get the ketone product. Okay, that's different than the hydroboration, where we get the aldehyde product. So here, what's going on? Well, we're going to protonate here, and we're going to deliver water. That's fine. And again, this is the proton. This is our electrophile. It's going on this N carbon right here, and as positive charge builds up here, water can attack. I'm not drawing a vinyl carbocation. That's not stable, but what does this give us at that point? It'll give us hydronium ion and what? That hydrogen on there, okay? So it's the same vinyl hydronium ion, but what? Take off the water, or the proton off the hydronium ion, we'll get the vinyl alcohol, and again, tautomerization to the ketone version now. And that's because the electrophile in this case was a proton. It goes on the N carbon there. Water comes in the internal carbon where there's more positive carbocation character. And then a loss there and tautomerization. And that happens very rapidly under the acidic conditions. You can actually draw a mechanism for that. Not worried about that. So what do we say here? Between hydration, which is what we've got here, versus hydroboration. Okay, different things. These are two different processes, right? This one gives aldehydes, borane and peroxide, and water and acid gives hydration, gives a ketone product. We say that these are complementary. Okay? They complement each other. In what way? One gives one regioisomeric product, the aldehyde, and the other gives the ketone or the carbonyl at the internal position, ketone product. Okay, so those are different types of processes. Let's look at a couple different examples of this with complementary conditions. So let's have the same type of substrate here. How about cyclohexane alkyne here. For one side, we're going to treat with chlorine and then base. And on the other side, we're going to treat with water and acid. Okay? Now keep these reagents straight. You need to focus on reactivity with these new reactions, right? Hydroboration and then base or acid and water. And what type of alkyne is this? Well, it's terminal. It has a hydrogen right here. So we'd expect different reactivity here. Well, if we do the hydroboration here, boron's going to go on the end, right? Hydride's going to be delivered here, and then we'll have that vinyl alcohol. And then that will what? Tautomerize to what? To the aldehyde product. Okay. So yeah, you should have been guessing that or working ahead with me a little bit. And now the complementary product also does hydration, adds water across here. But what are we going to get here? Here are electrophiles the proton. We're going to protonate there, add water there. And when that tautomerizes, what product are we going to get? Not the aldehyde, but what? The ketone. Okay. So those are, again, complementary conditions with that same substrate, just like we saw before with one butane. It doesn't matter what else is on the molecules. The terminal alkyne, you can either form the ketone or you can form the aldehyde. Okay, questions on that? Let's do a couple synthesis problems, and we'll do a couple more synthesis problems when we do the review video for test 3, which will be shown tomorrow, date-wise. We'll keep track of that. This video, the URLs are always on in Learning Suite, so you can always keep track of them. But let's do some reactions here with some acetylene anions and maybe some functionalization of acetylenes. Now that's the great thing about acetylenes. There's a lot of ways to make them. They can be protonated and alkylated, used in SN2 reactions. And then these 4 reactions from chapter 11 here can also be applied to them. So let's see. Let's take butane. Let's treat it first with sodium amide. And then we're going to treat it with ethyl bromide. What is the product? So these are multi-step synthesis problems where you can examine them one reaction at a time and then think about what the product and what the intermediate might be. So if we react this alkyne with this strong base, what are we going to get? We're going to get the acetylene anion. The sodium cation will be in there. The byproduct is ammonia. Don't worry about that. But now our nucleophile is what charge right here? So what's going to be our product? It's going to be that right there. Okay. We could add another step to this. We could take this and treat with water and sulfuric acid. What do we get? Now this is an internal alkyne. It's symmetric. It doesn't matter where you put the water. We're going to get what product? We're going to get ketone and the rest of the carbons. Now keep track of carbons here. 1, 2, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, we could have put the ketone there. It would have been the same thing. And don't worry about naming ketones or aldehydes yet. We're not going to ask you about that. Okay, maybe nomenclature, a couple simple alkynes. But there's a 3-step really synthesis problem going from this. So can you imagine being asked the question, how do you go from this to that? Now that's another way to ask the question. We're giving you the final product and you got to fill in these steps. That would be a little bit harder. We'll practice those. There's some problems in your book too. Make sure you work through some of the problems. But the more reactions you know, the more complicated, sorry about that, some of these synthesis problems can get. We'll keep them at a reasonable level here. What else could we have done with this acetylene anion? We could have taken that and reacted it with epoxide. Okay, what would we have gotten there? Well, that acetylene anion could have popped open that epoxide, and then if we have a step where we work it up with some water, we get this alcohol here, adding 2 carbons there, from the ethylene oxide. So that's another thing to be concerned with, that type of reaction. Now I'd like to give you a much harder problem. So some of these simpler problems, 1 or 2 steps aren't too bad, and you'll master those pretty quick. Let me show you a synthesis problem that involves quite a bit more planning. And in fact, we're going to give you the final product, and then we're going to ask you how to make it. So let's see here. Oh, it's a lot of stuff on this one. Oh, and then 4 chlorides there. Now, how do you make that from simple materials? And sometimes we tell you from any reagent or material with 4 carbons or less. And then you add in whatever other reagents you want. Obviously, this has more than 4 carbons, so you've got to make some bonds here. A lot of times, these are easily done if you think about retrosynthesis. Maybe I haven't mentioned that word before. Retro meaning in the reverse direction, meaning if this is the final product here we're asking you about, what's the next reaction back, do you think? Well, there's a couple spots we could do this. We could talk about alkylating an alkoxide, or opening up an epoxide somewhere here. But over here we just have hydrocarbon. But right here with the tetrachloride, that should say something there. In fact, how do we make this? The first step back, the tetrachloride, remember they're actually just covered to do that. It would be what? From, that's right, the acetylene right there. So let's see, maybe this first intermediate back would just look like this. You have that acetylene and then the 4 carbons there. So count them up, make sure we got the right number of carbons. So going in the forward direction, what would this be? We'd have to add 2 equivalents of molecular chlorine. Yeah. So we're partway there to figure out this reaction. What else could we do here? Well, we've got some bonds here. We could think about this bond right here. Okay. So if we had this O minus and maybe a propyl leaving group there. So if we had propyl chloride as a leaving group, and we had O minus, maybe from an alcohol, okay? And we know how to deprotonate alcohols. We'd have to add that with what? We'd have to add it with sodium amide again, right? So we treat this first with sodium amide or sodium hydride. That would form the O minus. And then we dump in the propyl chloride and then do what type of reaction there? That's a primary position, charged nucleophile after we treat with base. So what would that be? SN2 reaction, okay? So not too bad there. We can already see how to make that bond and put the 4 chlorides on there. Well, what did we just talk about here? An alkyne with 2 carbons and an alcohol. What can we do there? Maybe that bond. And that would come from what? It'd come from the acetylene anion. We know how to form those now. And what do we need to add there to this acetylene anion? We need to add 2 carbons and an oxygen. What's the convenient reagent there? Yeah, epoxide again, okay? So we put in epoxide. And again, keeping track of the mechanism, then we have to, quench with water or have a proton source to get the neutral alcohol. That would be it. And I think you already can see how to make that. Let's just tie this together. We'd make it from the terminal acetylene. We would treat with sodium amide. Okay. Not TB toxide. Okay, TB toxide's not basic enough. Pull this in proton. That pK is 25, so you need something that's more basic than conjugate base from an alcohol. So that would be fine. You'd be able to form that and then dump in that in the second step. So how do we make that? I guess we've got to tie this whole thing together. We'd start with acetylene gas itself. We treat with what? Sodium amide. Again, strong base. And then what? We need 1, 2, 3, 4 carbons there. So how about this? Yeah, we could make it from the bromide there. Yeah, counting carbons is the key thing. So wow, how many steps is this? This is by far more than we've ever done. The tetrabromide kind of gives it away. This comes from the acetylene. The acetylene ether, the ether. We could have done this a couple different ways actually, but this one works. This is the one that's known when I looked this up a while ago. But if this alcohol is deprotonated, you can alkylate it, miss it too. This can be made from the epoxide, like that, and yeah, base, you can lose a couple spots. Okay, I think that's all we want to say for now. Make sure you're reviewing these chapters, doing your homework book challenge, do the rest of the even problems. You have time, do all the problems at the end of the chapters. Practice makes perfect. That's how this is going to work. We'll have an exam review video that I will do, and we'll post on the URL on Learning Suite also. You'll be able to view it on YouTube. Email me with questions. I'll include those questions, but I'll mainly focus on the sample test 3 to get you prepared for that. So very good. Okay, take care. We'll see you soon. Thank you.